In this presentation, I would like to discuss a technique for fast determination of concentrations of salt and hydrate inhibitors in an aqueous sample. The technique was developed through a joint industry project at Heriot-Watt University and then commercialized by Hydrafact. Hydrafact is a knowledge-based Heriot-Watt spin-out company formed in 2006. Hydrafact's main expertise are hydrates, flow assurance, and PVT. The technique that I'm mentioning here is basically measuring electrical conductivity and speed of sound in a 100 ml water sample. A device made based on this technique used to be called CV device. You can see a picture here. CV referring to conductivity and velocity, but after commercialization the name was changed to HydraCHEK. Gas hydrates are crystalline compounds formed as a result of combination of water and suitable size molecules at low temperature and high pressure condition. They resemble ice, but unlike ice, can form at temperatures well above zero. Their formation in oil and gas pipelines can result in pipeline blockage and serious operational and safety problems, as well as significant economical impact due to loss of production and the cost associated with blockage removal. This setup here sort of simulating cross-section of a pipeline. Here, water-gas interface is clearly visible. This is the temperature probe within the setup. There is obviously a thin layer of water on the glass surface. Now, you can see hydrate formation in this setup. As you can see, hydrate starts from gas-water interface and then spread around. The figure here shows the hydrate phase boundary. In general, this phase boundary depends on the composition of hydrocarbon and water phases. Hydrates prefer large and round molecules because the presence of large and round molecules minimizes the distance between the guest molecule and the host molecules, and that increases the attraction force. Therefore, for example, if we have isobutane hydrate can form easily because these are large molecules compared to, for example, methane and nitrogen. The other factor controlling the hydrate phase boundary is the composition of the aqueous phase. If there is any non-hydrate forming compounds dissolved in water, some water molecules are busy dissolving the compound. Therefore, less water is available for hydrate formation. That results in hydrate phase boundary to shift to the left. In general, the composition of hydrocarbon phase is constant. It doesn't change so much. However, the composition of the aqueous phase can be changed by injection of thermodynamic inhibitors or water or compound that can dissolve in the aqueous phase. This is the technique that industry uses for controlling hydrate formation. In this slide, you can see the hydrate phase boundary for a natural gas in the presence of condensed water and 5 to 35 weight % methanol. Here we have used HydraFlash 3.3 for our predictions. As shown in the figure, the hydrate phase boundary shifts to the left as a function of methanol concentration. Also on this figure, we can see several operating conditions. For example, assuming the seabed temperature, minimum seabed temperature is 4 degrees Celsius, and we can assume the initial reservoir pressure is 150 bar. So that's the worst condition in the beginning. And then gradually with depletion, reservoir pressure drops. So these are different operating conditions during the life of the reservoir. Normally, the concentration of inhibitor required is based on the worst operating condition, i.e. the lowest temperature and highest pressure, plus a safety margin, typically 3 to 5 degrees Celsius. Some companies also consider other factors, for example, injecting 20 to 30% more inhibitor to take care of non-homogeneous distribution of inhibitor. Also, inhibitor loss to hydrocarbon phases. Obviously, in the beginning of reservoir life, pressure is high, but the pressure will drop during to depletion of the reservoir. For simplifying this discussion, let's ignore the safety margin and non-homogeneous distribution. In such a case, we can say at early days of the reservoir, we need around, this is 35, this is 30, so we need around 32.5 weight percent methanol to avoid hydrate at the worst condition of 4 degrees Celsius and 150 bar. This reduces to around 30.5 at 100 bar, and then drops to 27.5 at 75 bar, and is reduced to around, say, 23 weight percent when the pressure is 50 bar. And when the pressure drops to 25 bar, the amount of inhibitor required is around 15%. So you can see that during the life of the reservoir, the amount of inhibitor required is going to change. Furthermore, we haven't considered here the local ambient temperature. We assume the worst condition of 4 degrees Celsius. Obviously, due to seasonal changes, the temperature can change. So, for example, here at 25 bar, if we assume a seasonal temperature of, say, 8-9 degrees, we don't have any hydrate problem, so there is no need for hydrate inhibitor injection. Later in the life of the reservoir, normally the water cut increases. This increases the pump rate for methanol to maintain the desired methanol concentration. Hence, the inhibitor cost increases. Furthermore, the produced water may have formation water in it. Formation water normally has salt in it, so it will increase the salinity of produced water. Salt can also be regarded as a hydrate inhibitor, although it is not normally added to water for hydrate prevention. Here we have assumed we have a salinity of 15 weight percent NaCl. This is the hydrate phase boundary for the same natural gas in the presence of condensed water, no salt. Here is 15 weight percent NaCl, here is 15 weight percent NaCl, 5 weight percent methanol, here is 15 weight percent NaCl, 10 weight percent methanol, and here is 15 weight percent NaCl and 15 weight percent methanol. Again, the same operating conditions are plotted here. We can see that in the beginning of the reservoir life, even if we have 15 weight percent NaCl, the amount of inhibitor is not adequate to prevent hydrate formation. So we need to add more methanol. So for example, something around 12% methanol is necessary. However, when the reservoir pressure drops to 100 bar, the amount of methanol required drops to 10%. And here, for reservoir pressure of 75 bar, the amount of methanol is roughly 7.5%. And then when the reservoir pressure drops to 50 bar, then the amount of methanol required drops to around 5-8%. And then for 25 bar, or even if I look at here, 35 bar, the amount of salt in the system is adequate to prevent hydrate formation, so there is no need for methanol injection. However, in many cases, the amount of salt is not monitored, and the amount of inhibitor injection remains constant. Now, injecting too much inhibitor can result in salt coming out of solution. So we would have salting out problem, or we could have salting out problem, but also it can have other problem. For example, product contamination. For example, the presence of methanol in the condensate, as well as handling, pumping, and storing large quantities of methanol. In fact, large quantities of inhibitor are being used for avoiding hydrate problems, resulting in extra capex like pumps, storage tanks, piggyback pipelines, and OPEX, cost of inhibitor, logistics, disposal, and damage to the environment and the product quality. However, despite all the above measures, that is injecting too much inhibitor, there are numerous cases of hydrate blockage in oil and gas pipeline. Now, the typical reasons for hydrate formation is changes into the system condition and process variables. It is also another reason could be equipment malfunction or human error. Probably the most common reason is changes in the water cut, because if the water cut increases and we are injecting constant rate of inhibitor, the concentration of inhibitor in the water decreases, and therefore inhibition effect is reduced. The other important factor is inhibitor partitioning in the hydrocarbon phases. And finally, off-spec inhibitor. For example, inhibitor is supposed to have a certain purity, and it doesn't have that purity. HydraCHEK was developed to both minimize the hydrate inhibitor injection rate and improve the system reliability. HydraCHEK is in fact an extra safety measure, ensuring that there is always enough inhibitor in the system, and warn the operator against changes in the system variables. Now, why do we inject too much inhibitor? In general, the cost and disruption associated with hydrate blockage is huge, and there is no simple, fast technique for determining the amount of salt and inhibitor. So by the time most of the techniques for determining salt and inhibitor concentration are time consuming, and it needs relatively well equipped laboratories. So by the time we get the result, the system condition may have changed. And there is a general belief that a bit of extra inhibitor does not harm anybody, and the cost is very small when the oil price is high. Now, ideally, we want to be outside hydrate stability zone, but there was no practical technique in determining hydrate safety margin. Now, what is hydrate safety margin? Hydrate safety margin is in fact the operating temperature, or the worst operating temperature or pipeline condition compared to hydrate phase boundary. So compared to hydrate phase boundary. So this difference can be called hydrate safety margin. Now this margin can be 3 degrees, can be 2 degrees. It can be decided by the company or by the operator. But to find out the hydrate safety margin, we need two pieces of information. We need the pressure and temperature profile along the pipeline, or we need the worst operating condition. Then we need hydrate phase boundary. Hydrate phase boundary, to find hydrate phase boundary, we need two pieces of information: composition of hydrocarbon phase and composition of the aqueous phase. Composition of hydrocarbon phase in general is relatively constant, and it doesn't change in short time intervals. So if we can find the composition of aqueous phase, we should be able to find the hydrate safety margin. Now, so what we need is a quick and fast technique for determining the composition of aqueous phase. HydraCHEK is designed to do exactly that. HydraCHEK determines temperature, electrical conductivity, and sound velocity in a water sample. So this is the temperature probe and conductivity measurement, and these are parser and receiver, split out sound parser and receivers. The readings goes to a computer program. Now the computer program will give inhibitor and salt concentrations. Knowing inhibitor and salt concentration, we can plot the hydrate phase boundary. We already know the pipeline condition or the worst operating condition. So if the hydrate phase boundary is represented, for example, here by red line, so the pipeline condition or the worst operating condition is inside hydrate stability zone. So there is a higher risk of hydrate formation and blockage. If the hydrate phase boundary is represented by this pink line, we are outside hydrate stability zone, but the safety margin is very small. If it is the green line, that's probably the ideal condition, that we are keeping a safety margin away from the hydrate stability zone. We have a safety margin, and at the same time we are minimizing inhibitor injection rates. But if the hydrate phase boundary is here, it is very far away from the worst operating condition, pipeline condition. So we are injecting too much inhibitor. So we can easily reduce the amount of inhibitor to minimize the environmental impact and the cost. If you want to see how HydraCHEK works, please visit these videos, these links, and look at the videos. Conventional inhibitor and salt concentration techniques, they require the use of multiple techniques to find out the concentration of salt and inhibitor. There is no technique that can simultaneously give us the concentration of salt and inhibitor. Some of the techniques are, for example, GC, densitometer, titration, colorimetric. All these techniques, they have their limitations. HydraCHEK is basically a dedicated purpose-built instrument to simultaneously measure inhibitor and salt concentration in produced water samples. Some of the benefits of HydraCHEK are it's portable, it's very rapid, we're talking about a few seconds, it's cheap and robust, and can be used by non-experts. It can measure inhibitor and salt simultaneously. There is no specific sample preparation, but also it can be automated. HydraCHEK has been deployed around the world from North Sea to the Middle East. wide range of companies, oil and gas companies like Total, Statoil, Petronas, Dolphin Energy, and others, they have used HydraCHEK. It has been used for kinetic hydrate inhibitor injection optimization, for methanol and MEG injection optimization, for methanol and MEG removal regeneration plants, and monitoring of quality of water before disposal. There is an online version of HydraCHEK also that can take sample, measure the concentration of salt and inhibitor, and then dispose the samples into the pipeline. This is a lab-based HydraCHEK that can be installed in any lab or any room with positive pressure, air pressure. Here we are, the case studies of HydraCHEK are mentioned here. Now, 4 of these case studies have been published. Here we have the details of the publication, and if you require further information on this publication, please do not hesitate to contact us. Now, 4 of these case studies are presented here. Case 1 is a North Sea lean gas and methanol and Ceylon formation water system. The task is monitoring hydrate safety margin and hydrate slurry concentration. Now here the system was operating mainly inside hydrate stability zone. The operator knew that around 10% slurry, 10% hydrated slurry in the water does not result in blockage. So they were using HydraCHEK to make sure the concentration of a slurry is around 10%. For example, if the background water salt concentration is 4.5%, if 10% of water is converting to hydrate, because hydrate excludes salt, the concentration of salt in remaining water increases by 10%, which will become around 5%. So if the concentration of salt goes above 5%, it means that more than 10% water is converting to hydrate, and then operator needs to do something about that. Now with this technique, inhibitor dose rate was reduced to 0. Now that prevented, first of all, it saved a lot of inhibitor cost, prevented product contamination, and increased the life of reservoir, because the water production was the limiting factor in this reservoir. They could not maintain the amount of inhibitor required. This resulted in a significant extension to the life of the reservoir. Another case, North Sea lean natural gas and methanol and Ceylon water system. The objective here was to monitor and optimize inhibitor injection rate. Inhibitor dose rate was reduced in stages while monitoring hydrate safety margin. And finally, they managed to reduce the amount of inhibitor from 28% design to less than 5%. And obviously substantial direct saving in methanol cost, estimated at millions of pounds. Another case, Middle East sour gas condensate, where kinetic hydrate inhibitor was being used. The objective here was monitoring and optimizing hydrate inhibitor dose rate. The inhibitor dose rate was successfully monitored and optimized, avoiding potential hydrate blockage and direct saving in the chemical and lab cost, leading to thousands of US dollars. Another case, Middle East again, a sour gas condensate and MEG and produced water system. Monitoring and optimizing inhibitor dose rate. Inhibitor dose rate was successfully monitored and optimized to avoid potential hydrate problem, direct saving in chemical and staff cost. These are some of the success stories of HydraCHEK and the quotes. These quotes have been taken from the papers I mentioned. For example, Dolphin Energy. This automated HydraCHEK has allowed Dolphin Energy to rapidly monitor KHI present in the waters at the reception facilities, and in its own manner has then contributed to the success of KHI deployment in this field. South Park's gas complex, the field evaluation result of measuring unknown concentration of MEG and salt over a wide range of concentration were in very good agreement with GC results and far better than densitometer technique. Nuggets in the North Sea. Results show that HydraCHEK reported more accurate measurement of methanol and allowed for real-time determination of salt content in the field laboratory. Furthermore, HydraCHEK was faster compared to the manual technique and eliminated the requirement for chemical reagents. HydraCHEK has allowed North Alwyn to rapidly monitor the degree of hydrate inhibition present in the nuggets produced water at reception facilities, leading to an increased confidence in optimizing hydrate treatment. HydraCHEK also has been instrumental in several awards. Hydrafact activities, in particular HydraCHEK technology, played a major role in the Heriot-Watt University winning the Queen's Anniversary Prizes in 2016 for innovation in oil and gas sector for increasing productivity and reducing contamination. This was because HydraCHEK play a major role in extending the life of gas reservoir by 6 years, reducing methanol injection by 28,000 cubic meter per year, eliminating the need for a depropanizer. Another one, Hydrafact activity, in particular HydraCHEK technology, were recognized as one of the top 10 examples in the UK on the role of chemical engineering in modern world in 2016. And finally, Hydrafact activities, in particular HydraCHEK technology, played a major role in Heriot-Watt's Research Excellence Framework Impact Case Study submission in 2014. Finally, I would like to thank all the project sponsors that supporting this project over the years. Finally, please do not hesitate to contact us if you require further information or interested in field trial of HydraCHEK. Thank you.